Hi, I'm Dr. Courtney with the Quantitative Reasoning Center, and today we're going to work a problem on applications of multiple integrals. But before we do, I wanted to talk briefly about the fifth frequently fatal freshman physics fantasy, which just says simply, it's the fantasy that passing is more important than learning. And the things that you'll learn in Calculus 3, like many of your core technical classes, are very important because they build upon one another. They're essential skills for officers in the Air Force. In particular, skills that you learn in Calculus 3 and just the ways of thinking in multi-dimensions are going to be applicable in Physics 215, in Math 346, that's engineering mathematics, as well as a variety of higher level engineering and math and physics courses. Personally, everything I do in terms of the math and the physics and all the different skills help me professionally all the time just because it keeps my mind in shape. As they say, the math class is the weight room for the mind. Alright, so we have a non-trivial problem, and it tells us that a lamina is located inside one circle and outside another circle. So that's the region of space in the xy plane that we use to represent the area covered by the lamina. And we want to find the center of mass if the density at any point is inversely proportional to the distance from the origin. So we've already kind of interpreted that in our restatement of the problem, that the density is equal to k, or proportionality constant, divided by the square root of x squared plus y squared, which we're using as the distance from the origin. Okay, so our big idea here, or to interpret the problem, we're going to use integration along with the formulas and the definition of center of mass to compute x bar and y bar. And what these are is, this is the nomenclature that the book uses for the coordinates of the center of mass, because computing the coordinates of the center of mass is the same as computing the center of mass. So to develop the problem, let's go ahead and make our plan, and we'll worry about our picture here in a minute. First thing we need to do is we need to determine the region of integration, because the formulas for center of mass basically tell you that you integrate over the whole object. So we integrate over the region covered by the object. So we kind of need to express, first, what is a lamina? A lamina is just a thin sheet of material cut into a certain shape, so you can pretend that it's very, very thin, and you can treat it as a two-dimensional object. So in computing its center of mass, we only need to integrate over 2 dimensions rather than the third dimension, because the third dimension is trivial, being very, very thin. So determine the region of integration in the xy plane. And this has some sub-steps. We need to end up drawing a nice picture, but this isn't trivial because graphing this circle here isn't trivial. So first we want to complete the square to graph the first circle. And then we also want to graph the second circle. That one's a little easier because it's just x squared plus y squared equals 1. And then we need to look at that graph to determine the limits of integration. And these sound like simple steps, but we really need to keep our thinking caps on through the process. And now, the second step is we need to compute the mass, because the formulas in the book for the x and y components of the center of mass, or the x and y coordinates of the center of mass, include the mass. So we need to compute the mass first. And so there's two steps here. First we need to express the integral. In other words, we just need to apply the things that we know in terms of the formula that's in the book, and then we need to evaluate the integral. And we'll use Matlab for that. Once we have the mass, then we can compute the x-coordinate of the center of mass, and that's another double integral. But all three of the integrals that we need to work in this problem have the same limits of integration, which is why we spend the first half of our effort in expressing those limits of integration. So we express the integral and we evaluate the integral here, and then finally we can compute the y-coordinate of the center of mass. Whew. Man, I'm tired just thinking about it. Alright, so let's think about completing the square. So we get to our evaluate phase. And it's unusual that we don't try and draw a picture or draw a graph earlier. Why are we waiting so long to draw the graph? Why are we waiting to our evaluate phase? Well, that's very simple. I can't graph that just on the top of my head. Maybe you can, in which case you could have drawn the graph earlier, but I need to complete the square first. So x squared plus y squared, let's subtract the 2y from both sides, plus blank equals blank. And we need to put a blank on both sides so we have a perfect square. And I can see that that's 1. So we have x squared plus y minus 1 squared is equal to 1. Now I know what this is. This is a circle of radius 1 centered at x equals 0 and y equals 1. So now we can go ahead and graph our region of integration here. So maybe it'd be good to proceed with two colors. So the circle is x equals 0, y equals 1, and the radius is 1. So think about where the circle's going to go. It's going to kind of... that was a pretty poorly drawn circle. Let's go ahead and try drawing that one again. Sometimes you can get by with a rougher sketch, but that was just a little too rough for our purposes in this problem. So I need to turn that corner a little quicker, don't I? Alright, that might be about as good as I can get it without a compass or something like that. So this is one of our circles, and now we need to graph x squared plus y squared equals 1, and that's just a circle centered at the origin of radius 1. So now we have our two circles, and we're interested in the region inside the top circle and outside the bottom circle. So it's kind of this region here. And it's important to note when we think about our region that if we were to be tempted to set up these integrals from here and work them in Cartesian coordinates, we'd have to be very careful because we'd integrate from curve to curve. And unlike a lot of the integrals that we do in 2 dimensions, this region we need to set up 3 different regions to cover the whole area, because if we just start at the lower curve and go to the upper curve, and if we take the lower curve as something like this, and we go forward and say, okay, the lower curve is y is equal to the square root of 1 minus x squared. And if we integrate from the lower curve to the upper curve, and from x min to x max, we'd actually end up leaving out these 2 regions here, and we'd only end up incorporating the region in the middle. So for that reason, we want to employ polar coordinates in our solution. Alright, so now that we know that we're going to use polar coordinates, we need to think about how to express the limits of integration in polar coordinates. Well, if we think about our lower limit of integration, what's the equation of this circle? Well, the equation of the lower circle is just r squared equals 1, which we can also write as r equals 1, taking the square root of both sides because we're using the upper circle. Now, the upper half of the lower circle. Now, if we think about the upper, we could start here, but it's actually a little more instructive to start here because we can substitute in x squared plus y squared is r squared, and setting that equal to 2y, y is r sine theta. So now one of the factors of r's cancels out, and we end up with r equals 2 sine theta as the equation of our upper curve. So our limits of integrations are going to be r min is r equals 1, and r max is going to be r equals 2 sine theta. And now we need to consider the limits of integration for our angle theta. Well, we're integrating from this angle to this angle through this region here, and it takes a few minutes to do, but if you set, for example, the equations equal to each other and solve for theta, you can determine pretty quickly that theta min is pi over 6 and theta max is 5 pi over 6. And that comes out of the fact that the coordinate of this point of intersection is the square root of 3 over 2 1/2, and the coordinate of this point of intersection is negative the square root of 3 over 2 1/2. And then when you take the inverse tangent of y over x for those 2 points, these turn out to be the angles. Okay. Well, now we can move forward and we can set up the actual limits of integration. Well, the first integral we need to do is the mass integral. And by pretty much the definition of mass, if you use the definition of mass or the definition of density, the mass is the integral over the region of the density and then over the area. Well, in this case, we're integrating in polar coordinates, so we can express the density not in terms of x and y, but we want to express the density in terms of r and theta. And we can recall that in terms of x and y, the density was k over the square root of x squared plus y squared. So in polar coordinates, it's just k over r, which makes perfect sense because the density, it said in the problem, is inversely proportional to the distance from the origin, and the coordinate r is the distance from the origin. So the density is k over r, dA is r dr d theta, r min in this case is 1, and the upper limit of integration in r is 2 sine theta. The lower limit of integration in theta is pi over 6, and the upper limit of integration is 5 pi over 6. Okay, and before we go over to MATLAB and work this integral, let's go ahead and set up the other 2 integrals, the integrals for the x and the y coordinates of the center of mass. Because those are pretty straightforwardly related. Those are related in a straightforward way to the integral that we already have, because x bar is equal to the integral over the same region, so the limits will all be the same, and you get an r dr d theta, but they're equal to the integral over the density, which is k over r, now times x, but we need to express x in polar coordinates as r cosine theta, so you get an extra r cosine theta. So one of the factors of r's is going to cancel out, but the other factor of r does not, and the limits of integration are going to be the same. And in a similar way, the y-coordinate of the center of mass is going to be k over r sine theta, because this is where we're plugging in for y in the center of mass formula, and then r dr d theta. So these are the three integrals that we're going to work in MATLAB. Alright, well, what are we expecting? Before we go over to the computer, let's go ahead and use the time over here to think about what we're expecting. We've got the intersection of two circles, and we want the center of mass of a region like this. And well, what we're expecting is that the x-coordinate of that center of mass is going to be 0, and here's why. You have as much of the lamina on the left side as on the right side of the picture. So it's going to be balanced on the y-axis. So the x-coordinate of the center of mass we're fully expecting to be 0. Okay, well, what about the y-coordinate of the center of mass? We're expecting the y-coordinate of the center of mass to be greater than 1 and less than 2, because we're expecting that y-coordinate to at least be somewhere on the lamina. So these expectations are what we're going to use after we get done with the evaluation to assess whether or not our numbers make sense. Okay, so here we have MATLAB up and going, and we need to enter a sequence of commands to evaluate the integrals of interest. So let's go ahead and let's begin with the sims, and we're going to define r, theta, and k as our real variables, and r and theta are our variables of integration. So the first thing we need to do is we need to evaluate the mass integrals. So we want to first work the inside integral for the mass, and that we're going to use the in command, and the inside integrals, the integrand in this case is k, and it's over the variable r, and r goes from a minimum value of 1 to a maximum value of 2 times sine of theta. And now the mass is, you could also call this the outside integral, but let's call it m because we're going to divide by the mass in a moment, is the integral. And the integrand in this case is the inside integral from the earlier operation, integrating over the variable theta, and it goes from pi over 6 to 5 times pi over 6. So the mass works out to be this complicated expression here. It depends on pi, got a square root in it, and it's proportional to k, because k was our constant of proportionality. Now the constant k, because it's in the density, is also going to show up in our other integrals, but since the coordinates of the center of mass end up being divided by the mass, the constant k is going to get divided out. Alright, now let's think about the x coordinate of the center of mass. The inside integral for that, in that case, is going to be, well, it's very similar to the inside integral we computed a moment ago, except the integrand we end up multiplying by r times cosine theta, because it's not just the integrand, isn't just the density. The integrand in this case is the density times the x-coordinate, or r cosine theta. And now we can go ahead and the outside integral, and let's go ahead, we have to work the integral, and then we also divide by the mass. And as we were expecting from symmetry considerations, the x-coordinate of the center of mass is 0. Alright, Now let's consider the y-coordinate of the center of mass. And for the inside integral, the only difference between the x and the y coordinates is the cosine from the x coordinate becomes the sine for the y coordinate. And then the outside integral is the same, except it uses the different inside integral, and that works out to be this complicated expression, and in fact suggests that it's negative. Well, a negative answer wouldn't make any sense, but we also have a negative here and we have a negative here, so we need to consider that perhaps this whole expression in the denominator is negative, which would render the result positive. Alright, so we can use the eval command to get a decimal approximation for the y coordinate of the center of mass. So the y coordinate of the center of mass is 1.2645, which agrees with our expectation that the y coordinate should be between 1 and 2, because the y coordinate of the center of mass should be located somewhere actually on the lamina. So it's satisfying that it is. So the x coordinate of the center of mass is 0, the y coordinate is 1.2645, at least to that many decimal places.